I could have come up with a much safer sound effect for that starting point there. So I employed my 8-bit video gaming strategy walking in from the parking lot this morning because the lots are completely filled. So I had to park by the field house, and I used the 8-bit shortest distance, go forward a little bit, then over through cars. And I totally beat the lady who thought she went all the way over the yard. Proved it.
You had the hoverboard still.
Yeah, well, that's true. Well, I still have it. But the battery, those things are pieces of junk. The battery didn't even blow up on me. It just stopped working. Like it won't hold a charge. I found that out the hard way.
Did campus safety say you can't have it?
Yeah, they chased me off campus. Literally chased me. They were running down the hall, and it's like, you have to catch me first. I think it goes 10 miles an hour. They're not going to catch me. I mean, Usain Bolt probably could, but that's like it. How fast does he run?
I mean, 10 miles an hour is a 6-minute mile. He can definitely run a lot
faster. Oh, you're faster than that.
Mile.
So, yeah, so he would catch me. Yeah, but the campus safety guys, they couldn't keep up. Yeah, nothing. But yeah, I got on it at home. This was actually right after I came back from Israel. And I'm guessing, because I always had it plugged in, I'm guessing that just wore the charger out or something. But I don't know. I only had the thing for like 4 months. You wouldn't think that would happen. So I get on and everything seems fine, and then just shut off. And I'm on hardwood floor in the middle of a living room with glass coffee tables and stuff. So I forced a fall into the couch. Yeah, it actually looked way more graceful than it should have, but yeah, so nailed it. All right, so how did the Code Academy assignment go? Everybody get through it? Not horrible. Decent review. All right, did you learn anything new from that we didn't talk about last semester?
It was pretty short.
Okay, but a review. So you saw a couple of things that we did before. All right, good. So let me give you yours, just so I don't forget, your assignment for this time around. So actually, I want to take a break from... You guys should have the conditionals and control flow unlocked now, right? This guy?
Yeah.
How many sections are in that? I guess I should probably actually go through this so I can unlock it and see what you should be doing. Because this is kind of what's coming next for us anyways. It's unlocked for you?
I'm sorry.
You're doing that. So for everybody should have the book now? We all have the book? Huh? 11, so it looks like it's about the same length as the other one. All right, so... Okay, yep. So for your homework assignment for Tuesday, let's do the same thing we did for Unit 1. Go through Unit 2, take the screenshot. And then also, I want to give you a reading assignment. This will kind of be catching up, so going through the book. So this will be, if you go into the book for 250, go through chapters 1 and 2. So these two, most of that you'll be able to kind of skim through, just do the exercises, that kind of stuff. I would think it would probably take you less than 30 minutes to kind of go through it. But as you go through here, there are little quizzes and things like that that you take, little short little things that, answer these, 4 questions, that kind of stuff. All right, so go through, complete the portions of the book. That could be topic for quiz or something like that, so that's not a graded exercise. That's more of a kind of keeping up with the class from a different angle perspective. But the official homework assignment that you need to submit something for will be the Code Academy assignment for right now. Make sense? And I'll put that up on Blackboard after class. I just didn't want to forget it. And my homework will be to, I'll catch up to you real quick and on Code Academy. So hopefully I can pull it off. Okay, so let's get back to what we were talking about last time. We'll kind of finish our discussion about primitive types quickly, and as we kind of look ahead to the textbook here, we're sitting, so we're kind of already past the introduction to Java. So really, this chapter 1 and 2 thing is solving a similar thing to what you did with Code Academy for your last assignment. Kind of taking what we did like the last, let's say month of last class and reviewing it to kind of get you back up into what is Java and what does it look like, that kind of stuff. So we're kind of sitting right here somewhere in the middle of variables and assignments right now as I'm talking about primitive types. So this should all be, reviewing type stuff. There might be a couple of new things in there that we didn't necessarily discuss last semester, but for the most part, it's going to be review. Or if it isn't review, it's stuff you need to know. Okay? So in any case, and then we're going to be getting in with chapter 3, getting into branches. That's what's a Boolean expression? How do you use those things? If statements, switches. I'm not a big fan of switches. We'll talk about it, but I probably said that last semester. But in any case, we'll pretend like last semester didn't happen for most of your brains. But this is really our if statement section. Then we get into our loops sections. Remember we talked about how do human beings solve problems? We use our memory, we ask questions, and we do repetition. And those guys effectively are chapter titles here, right? So memory, ask questions, repetition. All right. Then we get into the storage of things. So that's when we get into arrays. And I think we dealt with arrays a little bit last semester, right? We definitely dealt with it on Alice, where we had collections of things, and I think didn't we have our monkey kings? Yeah, we had an array of monkey kings. So we'll start reviewing that, and then we really start getting into kind of new material. So I'm going to skim through this stuff fairly quickly, and you can read through things. If you have extra time and you want to keep going through the book, your next reading assignment is going to be branches, and then the one after that's going to be loops. So if you happen to be bored and want to just keep zipping through, that's all kind of review material. Well, at least we half review material. And then our new stuff really comes in starting with let's say chapter 5, as we kind of go through this, and then we're going to start getting into Android stuff the second 8 weeks. Okay, so let's jump back here. So last time when we were talking about primitive types, right near the end of class, we had this discussion of why do we have so many different ways of storing whole numbers, bytes, shorts, ints, longs, and kind of our punchline is kind of that it goes back to that Y2K bug argument where memory used to be really, really, really expensive years ago. So in our older language, since this language is based off of C, and just to give us a reference point, let me just draw that picture from last semester that kind of shows our evolution of our languages. I'll just draw the right-hand side of it for our high-level languages that we're kind of working with. So we have C, and when you read the introduction chapter in the book, they talk about kind of the history of C. So I kind of reference C as being 1968. I think the book kind of talks about it from 1978, but it really was the advent of the Unix operating system. Whatever, doesn't matter. So we have C, we have C++. We have Java. We have C#. We have Objective-C. I'm just not even going to put Objective-C 2.0. And then down here, we have Swift. All right, so these are kind of our high-level, object-oriented, general-purpose, what other qualifier will we put on this guy? Strongly typed programming languages. All right, we'll review what all those different things mean. All of these languages here all inherit a lot of stuff from this guy. So those primitive types that we're talking about right now that exist in Java, the decisions related to those were made right here. Back in 1968 when the memory was really, really, really expensive and very small in size. Okay? It's kind of interesting how the people have shuffled. You used to sit in a different spot, right? You sat over there, didn't you? Last class?
I sat there.
Oh. No, you didn't sit there. You sat one behind him. Really? No, I think both of you were lying. She definitely sat up there. Well, yeah. Now we got the friends together. It's all right. So, in any case, so all these languages, they made decisions coming from this guy right here. All right. So, getting back to this, so having so many different ways of storing whole numbers, positive and negative whole numbers, really came from the need of the programmer used to have to make that decision of what is the smallest memory space that I can have that will allow me to fit the data that I need to store, so that I'm being a good steward of my my memory, my computer memory. So it's kind of a similar thing that some of you have been having to deal with like the dorms. You got these little tiny closets in the dorms. That's your actual room is the closet, and you have to figure out where to put stuff so that it fits, right? Okay, you have a limited amount of space. So your dorm rooms are kind of like having 32K of memory, as opposed to today, our laptops, so you have a new release of probably, 8 gigs of RAM in that?
Yep.
Okay, so 12 gigs of RAM. Okay, so, plenty of RAM. He's not using 12 gigs of RAM in the thing, but who cares? It's cheap. Why not? Right? Why not have it? So the kind of the tables have completely flipped over today. So historically, we would have chosen one of these guys logically based on what we needed to store. Today, memory is kind of out of the equation for us unless we're doing some scientific research type stuff where we are just literally dealing with ridiculous amounts of data. If we're doing that, then technically you could run out of 12 gigs of RAM or something like that. But you can write the most memory inefficient business application and still have plenty of memory. All right. Now, having said that, you will very rarely today ever see anybody use short. Hardly ever. You might see it on the Google when you're searching for solutions to your homework assignments or something, because you might be looking at some old C code or something. But pretty much our go-to move as a Java programmer today is if we need to store a whole number, positive or negative, we put it inside of an int. If an int isn't big enough, we choose a long. If a long isn't big enough, then we go to object types like big integer or something like that. Bytes still technically do exist, but we don't use them for the reason of storing smaller numbers. We use them typically for like video streaming and stuff like that, where things are coming in bite-sized chunks. It's kind of the right size container to hold it. You put shoes inside of a shoebox rather than inside of like a kiddie pool or something. So something along those lines. All right, so now let's talk about chars. We'll review these guys. So chars are, and let me throw something in here. These guys are all signed numbers. So these are signed whole numbers. And what do I mean when I say signed? We talked about this last semester, so we'll do it as a review. When I say a number is a signed number, what does that mean? Nobody took the class last semester? Because, this slide is identical to what we built this slide last semester. Sign is positive and negative. It has a sign. It holds either a negative sign or a positive sign. Therefore, you lose a little bit of the byte space associated with it. So notice here, if this is an 8-bit number, because it's a signed number, only 7 of these bits are actually used for value. All right, let's talk about what that means. So under the hood, and this is something we're talk a lot about in the computer organization class. Under the hood, no matter, even though we like base 10 numbers because we got the 10 fingers, 10 toes things, computers like working with binary, base 2. All right, because on, off, 0, 1, it's a digital logic-based machine, so that's its go-to move. Well, human beings don't work in binary too well. We don't think in binary, mostly because we didn't learn binary when we were 4 and have been using it our whole life. It's not that binary is difficult or hexadecimal is difficult. In fact, it works the exact same way as our decimal number system. Last semester we did some conversion stuff, right? So it works the same way, but when we have binary numbers, this is what we're talking about with this idea of an 8-bit number or a 16-bit number or a 32-bit number. So when a byte is 8 bits signed, that means we have 1 bit for the sign, and we have 7 bits for the value, for a total of 8 bits. All right, so that means the smallest value that we can store in a byte is all zeros. The largest value we can store in a byte is all ones. All right, so now if I want to take this binary number of all ones and convert that to decimal, how do we do that? How do I take the number 1111111 from binary to decimal? If that were to show up on a quiz at some point. We had that quiz last semester, right? We're getting the deer in the headlight thing going already. Go ahead.
Well, you do like 2 to like whatever power. So like the farthest one would be 2 to the 0 power.
Okay. So if we
So
were,
be 1.
yep, so if we were to kind of draw this out, we'll draw little boxes here. Made that guy kind of squished. Oh, all is lost now. I lost the conformity. There we go. There's 2, 4, 6, 7. All right, so those are our individual bits. And this is 2 to the 0th power, 2 to the 1. I realize you can't see them. You will be able to shortly. 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6th. All right. Similarly, this is the 1's place, the 2's place, 4's, 8's, 16's, 32's, 64's. So 2 to the 0th power is a 1, 2 to the 1 power is a 2, 2 to the 2 power is a 4, so on and so forth. All right. Now, first thing is you don't have to memorize this, and the reason for that is you already count this way. Right? Let me just take a smaller version of this. So let's take the number 265. This is 10 to the 0, 10 to the 1, 10 to the 2, this is the 1's place, this is the 10's place, this is the 100's place. That's base 10. Exact same thing. We just use a 10 in the place of the 2 up here. Okay? So now, to convert this number up here from binary to decimal, what do we do? How do we get our answer here?
Add all those together, the 64 over the 1, add it
Okay, why are we adding all of them in this case?
Because they're all ones.
They're all
If
ones.
zeros,
So
we wouldn't
it's
add
really
them. Yeah.
1 times 1 plus 1 times 2 plus 1 times 4 plus so on and so forth. All right, so this is 1 times 1 plus 1 times 2 plus 1 times 4 plus 1 times 8 plus 1 times 16 plus 1 times 32 plus 1 times 64. Now we add all that together, what do we get? 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64. 127. Okay, so that's the maximum size value we can store in 8 or in 7 binary bits. Keeping in mind that one of these bits over here, we could just copy this guy, has nothing to do with the value. It has everything to do with the sign. So a 0 or a 1 would be a 0 would be a negative, a 1 would be a positive. It's just flags. Okay? That makes sense? So now we say with a byte value, so we're back here to a byte value, the range of values is negative 128, oops, sorry about that, negative 128 to positive 127. Now we just saw the positive 127, right? We just built it. So all those ones. To get the negative 128, the number is actually stored in something called 2's complement form. We're not going to talk about that in here. We actually will talk about that very soon in the 325 class. But the punchline is this. In computers, while we can subtract numbers, it is faster to add. So they've optimized the idea of addition. So underneath the hood inside of our computers, it's quicker to take a number and another number that we want to subtract from it, convert that second number to its negative equivalent, multiply it by -1. So to do that, we put it in 2's complement form. So it's not actually a multiplication. It's like you flip all the bits, so all the zeros become ones, all the ones become 0, then we add 1 to it. And then we add the two numbers together. So we're adding a positive number to the other guy's negative equivalent. Make sense? Giving us our final answer. Just a speed thing under the hood. We don't really need to we need to understand it in here just so we kind of know what's going under the hood, but we don't need to do it in here. I won't ask you anything about 2's complements. This is more of a, little note thing that you might put in on the side, just trivia knowledge. Okay, so we can take this exact same slide and expand it out for our shorts or our ints or our longs. You just have a lot more boxes. Okay? Similarly down here, how do we convert a decimal number to decimal? Well, first thing we would say is we wouldn't waste our time, right? But if we chose to waste our time, this would be 5 times 1 plus 6 times 10 plus 2 times 100. So that's 200 plus 60 plus 5, which is 265. Make sense? Identical. The exact same thing we did with the binary. We've been doing this all our lives. We just don't think about it like this because it's second nature to us. We're pretty used to base 10 numbers. We kind of know how they work. Okay? All right, questions about the binary, base numbers, all that stuff? So this directly translates back to this guy here, where we have all these different ways of holding whole numbers, and ultimately what it comes down to is how many buckets, how many bits do we have for representing the value portion of it. And every one of these takes up 1 bit of memory, okay? And in this case, this is 7 bits, a total of 8 bits with a sign, okay? Well, How many bits of memory are in our computers today? So let's say our average computer has 8 gigabytes of RAM. His 12 gigabytes is probably a little over the average, wouldn't you say? Okay, this one has. Does anyone have his laptop beat?
I have 16.
You have 16. Anybody have more than that?
I have 32
On your desktop. Yep. All right. So now this computer's from 2012. This is an older computer because I'm holding my breath waiting for Apple to come out with the new MacBook Pros. Yeah, but I still have you beat. Okay, so I have 16 gigs of RAM in this, which I promise you was extremely expensive in 2012, especially on these because they actually solder it on. You can't even upgrade the RAM in these. So you had to basically buy as much RAM as you thought you were ever going to need day one. That's the side effect of some of Apple's stuff. I mean, I'm a big fan of Mac laptops for computer science students, not because Apple's better, but because it's 2 computers for the price of, let's say, 1.7 or something like that, because you can dual boot and run Windows and Mac on the one machine. So now you have one tool that'll allow you to do kind of both sides of computer science, whether you're doing iPhone programming or .NET programming, you have one machine for everything. If you're doing everything on the Windows side, I mean, why spend $2,000 on a laptop when you can get equivalent performance for $900 or $1,100 or something like that if you want the bigger screen? So they're both cars. They'll both get you to work. It's kind of the punchline. But one of the side effects of Apple, I think, in some ways it's a positive side effect until you have to get something repaired. Then it's a negative side effect. Apple tends to always try to make things thinner and thinner and thinner and thinner. And what that means is removing replaceable stuff. So, for instance, Apple laptops haven't had replaceable batteries in a long time. Well, why? They can increase battery life by taking the space they used to have for the slide that allow you to slide the battery in and clip it in. They took all that hardware out, made the battery thinner, and made the battery longer to fill in those extra spaces. Great, so you have better battery life and a thinner laptop, but you also can't replace the battery yourself. So you got to go in and give Apple too much money for the battery, and then too much money to install it when you used to be able to just go on eBay and buy a knockoff battery and then swap it out in 10 seconds, right?
I think the mid-2012 was like the last MacBook Pro that you could actually do anything on. Like,
Yeah, well, so this is this late? No, mine's
late 2012.
Mine's
Really?
mine's mid 2012.
Okay.
Yeah.
It might depend on the model, but I know
Okay.
like the A1206.
This was the original Retina.
Gotcha.
This is the
I'm
original.
thinking of the non-retina.
Yeah, this is the original Retina MacBook Pro, and nothing's replaceable. The bottom of it is a solid piece of whatever Apple's made up aluminum or something. Isn't that funny in their commercials? They're like with the Apple Watches, they're like showing you how they've made these different metal alloys that they built. Do we care? What do we care if you found out a better way of making silver or something? Cut the price of the watch by $100. Just give me the old stuff. Yeah, I don't know. Okay, so in any case, these number systems, we're going to be coming through your computer science career, going through your degree program. You'll be becoming much more familiar with this stuff. I put a pretty high importance of understanding this concept, but we won't get much more familiar with it than this in here. Okay, other classes you'll become very acquainted with bits and bytes and hexadecimal and things like that. And I suppose just for completeness here, we'll just throw one more example out here. So I'll steal this guy. We'll pick my favorite hexadecimal number. Anybody remember what that is? Bad, yeah. All right, so hexadecimal is base 16. Well, so with decimal, base 10, our legal digits are 0 to 9. Binary, base 2, our legal digits are 0 to 1. Hexadecimal, base 16, our legal digits are 0 to 9, then A to F. You know, you can't say 10, 11, 12 because those aren't digits. Those are numbers. They take up more than one little slot. All right. So we use A through F to fill out our hexadecimal thing. Okay, so this is 16 to the 0. This is 16 to the 1. This is 16 to the 2. This is the 1's place, the 16's place, the 256th place. A D is actually the number 14, an A is the number 10, a B is the number 11. That's what it ultimately translates into. So this would be D times 1 plus A times 16 plus B times 256. So we said B is an 11. 11 times 256 plus 10 times 16 plus 14 times 1. I've done something wrong. 11, 12. Oh, it's 13. 2989. There we go. So D is not 14, it's 13, because you kind of have to know your ABCs, but I'm a computer scientist, so I don't have to know those. It's for the English majors. Okay. All right, so yeah, D is the actual number 13. A, B, C, D, 10, 11, 12, 13. Yeah, nailed it. All right, so 2989 is our final answer for that guy. So if we were to convert this guy to decimal, BAD in hex is equal to 2989 in decimal. Fine. Realistically, the reason hexadecimal exists is we can imagine that if 2989 is this in 4 digits, can be represented in 3 digits here. As the decimal number gets bigger, the hexadecimal number probably stays arbitrarily smaller. So we can represent larger values in smaller footprints. That's kind of the concept of why hex is maybe used. Now, to move away from the idea of why human beings like that, why human beings care about that, the short answer is we don't. Hexadecimal doesn't do us any good until we get into the idea of digital logic. Just like base 10 doesn't do us any good with digital logic. Base 10 is effectively the way that computers communicate with us so that we can understand it, right? It'll convert it to base 10 so that the numbers make sense to us. Because if we just see a big stream of zeros and ones, even though we just proved that we could convert it, we're kind of lazy and don't want to, right? I mean, it's interesting to say that we can sit down and do it and like, okay, I'll get the credit on the homework or whatever, but it's good to have that skill. We don't want that. We don't want to have to do that. Human beings want just stuff spoon-fed to us, and that's okay. So really what it comes down to is computers like binary and they like hexadecimal. So it's really about converting between those two, okay? Decimal isn't even a thing in computers other than the fact that human beings are involved. So what's nice about binary versus hexadecimal, the value 0, well, let's say the decimal values that are represented in hexadecimal are 0 to 15, right? How could you represent the number 15 in binary? Is that 15? It's 14. So we can represent all of the hexadecimal values in binary using 4 bits, half a byte, which we call it in computer science terms, we call that a nibble. Okay? We don't care about that in here. We'll care about that in 325. All right? So punchline here is for BAD, we want the value of 11. So that's 8 plus 0 fours plus 2 plus 1. That's 11, right? Then we want the value of 10. 8 8 0 4s, 1 2 0 1s. And then we went 13, 8. Oh, sorry. That 13. Take the little spaces out. That's the binary version of bad. That's 2989 if we were to do the math. So converting between hex and binary is actually quite easy. We don't have to do any of the weird stuff because we just have to deal with it in 4-bit chunks. Make sense? So we kind of just saw under the hood why hex and binary are kind of involved there. Our third guy that's involved to a lesser extent is octal, and that's for kind of an unrelated reason. So we won't talk about it right here. We'll talk about it in your class.
That should be our 325 quiz.
That's your 325. Oh, what, this right here? Yeah. We haven't talked about it yet. Oh, you have had the discussion, so, right.
Our reading.
Well, it wasn't a reading.
This is pretty much our reading.
Yeah, that's true. It should be the quiz. Yeah, I didn't read that.
It's a lot about binary and types.
Don't you hate when a teacher gives you homework and doesn't do it themselves?
It's probably stuff. It's like...
Well, no, the worst part is when a teacher gives you homework and you don't believe they could do it. That's the bad one, right? It's like, why are they giving me this to do? I don't think this guy can do that.
Like, here's the 325 reading.
No, so I've memorized this.
Yeah.
I memorized that.
Yeah.
See, I don't need to read it. Nailed it. Okay, so that's kind of the whole hex to binary thing and then why it exists in computers. So under the hood, computers aren't speaking our lingo. We like the base 10 stuff, but the good news for us, and this kind of drags us back into the programming world, is this is why things like Java exist for us. So that we can talk to computers in a more English-like way than this. So fine, we can look at Java syntax and say this is all Greek to us or whatever. But the reality is would you rather write stuff in Java or would you rather write stuff like this? The correct answer is Java, right? It's closer to what we find intelligible than this. All right, so getting back over here. So these are all of our different ways of holding our whole numbers, and this is kind of the explanation of 8 bits, 16 bits, 32 bits, what that means, okay? Now we get to chars. A char is an unsigned. What does that probably mean? If signed means it can hold positive and negative values, what do you think unsigned probably means? Can't hold positive and negative values. Everything's positive. We don't take up a bit for a sign. We're not going to waste our time storing a sign because it doesn't make sense for this. So this is an unsigned whole number. And this guy in Java is 16 bits. Okay? Now, something that's interesting here, though, and we talked about this last semester, so I'm about to ask you why it works this way, is when we think about a character, we think about things like A and B and question marks and colons, things like that, right? Those are characters to us. Why would we represent them as numbers? Why would Java have the char primitive type, the variable type built for holding on to these characters, again, that human beings are used to working with? We like, well, especially Americans, we like the English symbols, right? The alphabet and then the question marks, punctuation stuff, and we have our numbers in there too as digits. The digit 1, the digit 2, can't do math with them, but it's the character representation of those. Why are we storing them as whole numbers rather than just storing the C or the A or the question mark? What?
Isn't it partly because it's a string-based language, so you can easily put things together?
Okay. No.
Yeah.
No, I mean, I think there are some true aspects of your wrong answer. Java is a string-based language, so we use characters a lot, but that's not really a Java thing. That's a human thing, right? We're all sitting in here, and I kind of even see a couple of you partially asleep right now, but generally speaking, I'm going to have a whole lot better chance of conveying this information to you speaking English than speaking binary, right? So human beings are kind of predisposed to natural languages, right? Do you have a wrong answer you want to give me?
I do things twice if they're set up for numbers. Why would they want to hold different systems for like letters and characters?
Okay. Also wrong, but not an unreasonable thing, right? Would you probably say, though, when we're dealing with computers, especially the things we've looked at so far today, that most of the things they've done, it seems to make sense, right? The whole binary hex is like really easy conversion between the two of them. That's probably why they picked base 16 as opposed to base 17. I mean, if one of the goals was to be able to represent big numbers in smaller spaces, why stop at 16? Why not go to base 34, right? I mean, you can go higher. You know, a base 34 number is going to be able to hold gigantic decimal numbers and even smaller footprints because they scale quicker, right? Because we have, 34 to the 0 power, 34 to the 1 power, 34 to the 2 power. I mean, those become big numbers pretty quick for representing those values. So it usually makes sense, but they purposely stopped at 16 because it was very compatible with our required base 2. I mean, why is base 2 required in computers?
It's what machine level can read.
Okay, but why? I mean, that's a true statement. Why is it that's how it works? This kind of goes back to this conversation of like, well, it kind of makes sense.
Yeah. Like switches are on or off.
Yeah, well, I mean, these guys are digital, right? These are digital animals. And digital means on or off, 0 or 1. We need to keep track of 2 states on a computer. So binary makes sense, right? Some of the new types of, if we kind of use our imagination to decide where computing is going, you maybe have heard of things called like quantum computers. So quantum computers are trying to move past that kind of base idea of what a computer is. Because really, we've been sitting with this technology for a while, and they keep getting faster and faster, and we come up with interesting ways of working with them. But do we at least suspect that we're maybe starting to hit sort of end of life of same old? Maybe there's going to be another jump where we go to something else. If you want to talk about it in kind of made up terms, we can say, well, maybe we'll move to base 3 logic. Okay, probably won't be that, but something along those lines. Like maybe we've run out of what we can accomplish with base 2. That's probably a misrepresentation. I don't think we're there yet, but I think we can get there at some point, where there might be some advantages of being able to represent things in 3 states instead of 2. Okay, so in any case, so get back to our question here of why are we representing characters as numbers? Okay, you mentioned that it's because, why reinvent the wheel and keep it same old or whatever. Well, computers like numbers. That's how computers store stuff. Specifically, computers store stuff in bits. They can only represent things in bits, 0 or 1. That's how they hold on to the state of something. So really, it's the other way around. Even though we like characters A, B, C, question marks, whatever, we have to have some way of representing those inside the computer as bits. Because that's all the computer can hold. It's just a whole bunch of little tiny buckets for holding zeros and ones. Quite boring from a human being's perspective. It's too granular for us, right? We like power tools. If we're out in the garage and we have to screw something in, do we go get the manual screwdriver or do we get the screw gun? It depends, how lazy we are, I suppose. But my experience has been, at least maybe this is for guys, you always get the power tool. And then my wife yells at me when I crack the little plate that goes over the light switch. Yeah, because you're really not supposed to use power tools in that. You want to hand tighten it so you don't crack it when you use the power tools. That's the exact noise it makes when you're about to get yelled at. I can tell you this from years of experience. Man.
So do you associate that sound with getting yelled at?
I associate a lot of things with getting yelled at. Yeah, but when you're I've been married 16 years, so I've realized that I'm not good. I've been properly trained. Let's see. Okay, so we need to represent these guys in bits at some level. So what we're going to do is we're going to take a 16-bit representation. So 16 zeros and ones. And we're going to use those 16 zeros and ones to represent our characters. Now, how many characters do we need to represent? Well, we need A through Z uppercase. Then we need our punctuation stuff. And then we need 0 through 9 for digits. How many total characters is that? Just roughly. Is that 54, 64, maybe punctuation is another, let's just say 10, 74, let's say 74. Why do I need 16 bits? How many of you speak a language other than just English? You know a second, third, fourth language? Several of you, right? So the whole world does not revolve around English, right? So we have more than those 72 characters that we need to represent inside of computers. We have to represent the character symbols from various other languages. Now, so this is something we call Unicode. This guy right here. So Unicode has 65,000, so this guy represents, let's just create another slide for this real quick. Unicode. So this is 16 bits, unsigned, signed, 0 to 65,535 is the range of value. So we have 65,536 unique characters that we can remember. And rather than representing an A in base 16 or representing a B in base 16 or in 16 bits in base 2, what we instead do is we use the Unicode character map. So we map binary values to a lookup table of equivalent chars. So character 32 will be something, character 33 will be something, so on and so forth. So we're mapping them together. Now, in the early days, so back in the C programming days, we didn't use Unicode, we used ASCII. So we're going to call this upgrade to ASCII. And ASCII was only 8 bits. So that means we had 0 to 255, so 256 unique characters. Now we just said that the English language has roughly 72, 75, just ballparking, less than 256, right? Unique characters in it. So what did we do to fill out the ASCII character set? If you've ever opened up a binary file on a computer, like you double-clicked on an executable, but you opened it in a text editor or something, you see things like smiley faces and like playing cards. Yeah, that's America for you, right? So we literally filled in a majority of our alphabet in ASCII with like symbols of like cards and smiley faces and things like that. Just random stuff that really has nothing to do with anything. Because the idea is like, oh, computers are for video games and stuff, so probably want to play card games. Kind of the punchline there. All right, questions about any of that? All right, so reading assignment is chapters 1 and 2 from the book. Do all the little exercises. I'll be able to see that you've checked those off. That's for our assessment stuff. Homework assignment is do the second section of Code Academy and do your screenshot thing again. Make sense? All right, I will see everybody on, wait, hold on. We're not done yet. This is Tuesday, Thursday. We got time. We're still going. You guys were just going to let me do that, weren't you? Jerks.
I didn't want to interrupt you or question your knowledge.
We got so much stuff to get through. You were going to cut this class short. We're at what 11:20?
Yeah.
Oh, we got tons of time.
I thought you were just done.
No. We're never done. Never done. All right, good. Well, so we reviewed our homework assignment. Now, And you've had a foreshadowing of what the end of class might look like. All right, so in any case, this is why we have characters represented as whole numbers. Okay, they're represented as whole numbers because we need to store them as binary bits. And then we just use a lookup table, and we've upgraded our lookup table over the years to recognize that other languages other than English exist. Is kind of the idea. Now, Unicode doesn't cover every natural language because there are a ridiculous number of natural languages in the world. I think in Africa or something, there's something like 1,400 different dialects or something. It's like something ridiculous. So let's say it covers our mainstream natural languages according to whoever decided they were mainstream. Let's go with that. All right, so lots of individual characters. All right, so we hold chars as whole numbers because computers know how to hold bits. That's the punchline. That's why this guy is a number. Floats, these are signed. Decimal values. And these are 16-bit, followed by a decimal, followed by 32-bit. No, I'm lying. Other way around. 32-bit, followed by a decimal, followed by 16 bits. So we have 16 bits for what comes after the decimal point. A double is almost the same thing, except it's 64 and 32. All right, so a double is 96 total bits to represent a double. All right. Now, a Boolean is a single bit. Okay, it's a single bit on or off. So 0 or 1. Now, the punchline here, though, is in Java, the smallest thing we can represent is a byte. So these are actually represented as bytes. So this would be that's our Boolean value, 0 or 1. Make sense? Now you'll learn in 325 that we actually have, under the hood, we have specific hardware registers that are 1 bit big for holding results of Boolean expressions. But from a Java perspective, things look like this. All right, any questions on this? All right, so there's Unicode, binary values, there's our pretty picture, hex to binary. Okay. So now let's review Boolean expressions. Definition of a Boolean expression is? No, somebody else. Go. Okay, so any expression that boils down to a single value of true or false. Expression that boils down to a single value of true or false. Okay, so that's all fine and dandy. That's a tool we might use. So we can represent things that ultimately boil down to trues and falses. We can represent things that ultimately boil down to numbers. Now, Boolean expressions are used in conjunction with Boolean operators. What Boolean operators do we know about? We have 2 different classifications of Boolean operators, so I'll give you a hint, but then one of you is going to answer this. All right, so what are our arithmetic Boolean operators? All of you have known these since something like 3rd grade or something like that. Huh? Okay, so greater than or equal to, less than or equal to, not equal to, those guys, right? Okay, so typically, if we were comparing two things for being is one thing greater than another thing, what are those things? So something greater than something else. What are the question marks? What kinds of values are those question marks? This isn't even a Java question. This is just like a real life question. Which is, do you want $5 or do you want $10? You want $10. Why? It's more than $5, right? So $10 would be greater than $5. So typically, and especially since this is in a category called arithmetic, these are probably numbers, right? Probably numbers. I'll just take the S off, but whatever. So some number greater than some other number, some number less than some other number, that kind of stuff. Okay, so those are our arithmetic Boolean operators. And ultimately, this boils down to true or false. A single value of true or false. Okay. Logical Boolean operators. What are those guys? Good. Okay. You're 3 slides ahead of me. So if else are going to use Boolean expressions. These guys are going to be Boolean expression based things. But logical Boolean operators, because inside of an if else we can use this less than, greater than, that kind of stuff. Go ahead. Okay, she's cheating off last semester's notes. Is that what happened? That came out of your mind? Oh. She's like all defensive. Like, look, I got this. All right, so this is our not and I'm looking for the key. First time on a keyboard. Just bear with me. So not 2 ampersands as an and, no spaces. 2 pipes, vertical bars, whatever you want to call them, with no spaces. That's an or. We actually have a couple other ones. We'll see if you know what these are. I don't know if I talked about these last semester, so we'll fill them in a little bit. We got this guy. We got this guy. And we got that guy.
Bitwise and bitwise or.
Okay, so these are bitwise and bitwise or. Did we mention those?
We did.
Okay. And we'll talk about those again here in a second. What's that guy? And one of the important reasons to show this is for many of us, and we've already used it in our examples today, when I wanted to say something like 10 to the second power, I put that little caret in there, right? That's kind of a human way of representing something to a power. When we don't have the right key or the software doesn't support the superscript thing to put it up there. But I promise you in Java that won't work. If you try to say int num is equal to 10 caret 2, you're going to get a not the value you expected. So what do you think this guy is? It's the exclusive or. The exclusive or operator. So we have and, we have or, we have XOR. And everything must be true. Or at least one thing is true for an or to be true. Exclusive or is exactly one thing is true. Okay, so exclusive or says one or the other, but not both. Realistically, we will rarely use exclusive ors in programming, but it does exist. Typically, if you want to accomplish something like an exclusive or, you'll just build a more complex looking and an or. All right. But know that it exists. And then the bitwise things, which we will also not use in here, but for information, these do exist. So bitwise and, bitwise or, these actually operate on numbers. Okay, so if I take the number 5 and I bitwise that and that with the number 7, I'm going to get a value. And the value I'm going to get is going to be the result of taking the bits that are 5. So how do I represent 5 as a binary number? It's a 4, a 0, a 1. So that's 5. And the number 7 is a 4, a 2, and a 1. That guy? Okay. So now to get the AND of those, we do it on a per bit basis. So this is a 1 ANDed with a 1 is a 1. A 0 ANDed with a 1 is a 0. A 1 ANDed with a 1 is a 1. So this is saying true and true is true. False and true is false. True and true is true. So the answer of 5 and 7, and what number is this guy? This is 4, no 2s, 1, so this is a 5. So 5 bitwise and with 7 is decimal 5 or binary 101. We don't have uses for that in the problems we're solving right now. I promise there are uses for that. Okay? But in any case, that's that. Similarly, I'll just introduce one other thing that we also likely won't use in here, but since we've been talking about binary a lot like this, we have shift operators. This is a left shift. This is a right shift. All right. So the way this would work is if I did something like this. If I took the number 5 and I left shifted it 2 times, we would take the binary value of 5, so that's 101, and we would left shift it twice, which means the 1 and the 0 would fall off, and we would be left with that. That make sense? So these two guys kind of fall off the ledge over here to the left. This 1 shifts to the left twice, and then we have a couple of zeros after that. Similarly, a right shift, 5 right shifted 2 times would be 101. Now we would have 0, 0, 1, 0, 1. But since we had a 3-bit number, that's our first first left shift, or our first right shift. There's our second right shift. Here's our original endpoint of our number. So these guys fall off. So it modifies the number. Again, we don't really have a use for that in here. There is a use for that in, I guess, real life, for solving some other problems. These things are used pretty heavily in like cryptography, doing number manipulation stuff. There's a mathematics called combinatorial mathematics that this kind of stuff is used pretty often in. But we won't be using it in here. This is more just know that it exists. I'll never ask you to do bitwise stuff in here or shift stuff. Just add it to your knowledge base. Okay. So really what is important to us, so I'll put these, we'll do this. Just call these guys extras. All right, so these are the important ones for us. an or, an and a not. What does not do? I can sit here in silence too. Somebody help me. What does not do? Go ahead. Okay. I think you said both things. So we have a not equals operator for comparing two numbers. This guy will return true if the number on the left and the number on the right are not equivalent to each other. Okay, so that's our not equals operator. Our not operator works directly on Boolean values. That is to say, not true is equal to false. Not false is equal to true. Not 5 less than 3 is equal to true. Is 5 less than 3? No, that's false. Not false is true. Make sense? So it flips the value of a Boolean. All right, so that's what not does. All right, so we're talking about Boolean expressions. In order to talk about Boolean expressions, we need to understand the Boolean operators that we use to build Boolean expressions. So a Boolean expression is any expression that boils down to a single value of true or false. So now we get to what he brought up, is how do we use these Boolean expressions? So in and of themselves, Boolean expressions are maybe not completely useless, but not that interesting. We need to use them in conjunction with something else in order to accomplish real things. So we have our conditionals. Just like we talked about last semester, the way human beings solve problems is memory, asking questions, repetition, variables, conditionals, loops. That's our programmatic representation of those things. All right, so conditionals are accomplished really two ways in Java. I focus on one. You'll read about the switch in the other one. I just think it adds, I don't like it. So we have if statements. So an if statement syntax in Java is the word if, all lowercase, followed by an opening parenthesis, followed by a Boolean expression, followed by a closing parenthesis, followed by an opening curly brace, followed by a list of statements, followed by a closing curly brace. Optionally, we can have a else, all lowercase, followed by an opening curly brace, followed by a list of statements, followed by a closing curly brace. All right, if we want to see an example of this, and actually let me quickly, we didn't actually put this in the slide, I kind of just assumed it. Variable syntax. We have type, var name, equals value, semicolon. Type, so it can be any primitive type, so all the things we talked about today. That would actually make a good quiz at some point, is list all the primitive types. Byte, short, int, long, char, float, double, Boolean. That'd be a good quiz. Maybe a upcoming quiz, a very... All right, so it can be any primitive type. It could also be any object. type. And right now, in terms of what we discussed so far this week, we haven't discussed any object types. Last semester, we did work with strings, which are object types. Okay? So literally, this guy right here could be an infinite number of things. And the reason for that is, in Java, we can create our own objects. And we saw this last semester when we first started transitioning from Alice to Java, where we kind of mimicked our Alice program using Java objects. So we had a Monkey King object. So we didn't really talk about it from a theory perspective, but we saw it. Okay, we saw how we could just. We're all pretty sure that the Java language didn't ship with Monkey King built into it, right? Probably not a thing that was built into it. So we can make our own objects, and therefore we can create variables of our own object types. But this is the generic syntax for a variable. So now if we're looking for an example here of, let me justify this. So I might do something like int a is equal to 5, int b is equal to 7, if a is less than b, we might do something, else we might do something else. Okay, remember inside of here would be a list of statements. So this is do something when a less than b. So this is a comment. This is a single line comment in Java. Multi-line comment would look like this. Do something when a is greater than or equal to b. So that's where the else would come in. So we have a couple of variables. We ask a question. If the answer to this question is true, then we do whatever is between this opening curly brace and this closing curly brace. Else, which is optional, we can do something else when this is not true. Make sense? Now, technically, in Java, these curly braces are not required. And what I mean by that, if we were to be completely truthful here, the actual thing this line should say is that. If Boolean expression followed by a statement. That could be a single statement, or the commonly used statement is something called the block statement. And the block statement looks like this. Now, having said that, it is never, ever, 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 ever incorrect to use a block statement and put 0 or more statements in there. It's never wrong. So I encourage you to do this. And the evidence would be all the way back here in our most modern language, let's say Swift, which has taken everything into consideration from these older languages, as well as all these web languages that we had over here from last semester. And its if statements require the opening and closing curly braces. It is part of the syntax. They're basically saying, fine, we get it. You don't have to use the opening and closing curly braces if you only have one statement to execute. But you know what? It adds some structural integrity to your code. Makes it look a little cleaner. And it's never wrong. So I would strongly encourage you to get into the habit of always doing this. Opening, closing curly brace, even if you only have one thing to say. Make sense? All right, so now we're out of time, right? All right, all that crap I said before. All right, I will see everybody on Tuesday. I do have the link up for the videos on Blackboard. I also have a link up for the slide set. It should always be up to date. It's saved through iCloud, so it like opens up in our webpage. All right, have a good weekend.